Hello everybody, welcome back to my channel. Today is the 29th of December and it's like 10 o'clock at night and I'm back at home. I know it's been a while since I've last made a video. It's been a mix of I've been flipping busy as heck in the semester and I've been going out during the holidays, and also a little bit of I'm too lazy to record, and that is obviously partly my fault. But anyways, I was revising some maths topics in like the linear algebra section, and I remembered a while back that one of my friends was struggling on determining the rank of a matrix. I'm also recovering from a cold, that's why my throat and voice might sound a bit like croaky. Yeah, I'm not a smoker, but anyways, I have three different types of matrices here. All of them resemble different things just for like learning purposes. But we have three different matrices. The first two are 3 by 3, and then the matrix C is a 3 by 2 because I'm doing like rows and X columns, right? So we'll start off with A. So there is actually more than one way of finding the rank of a matrix. The first one is like using row reduction and seeing how many rows or columns have a full column or row equal to 0. It's either or. So you'd like basically try and make all of these 0, and if you can only get one row or column equal to 0, then the rank of that matrix will be 2. I would be covering that just because there's another more efficient method which I'll be covering, and that's the one that my module uses, well, for the final exam anyway. It's just we're taught the first method for the first few weeks because we're not taught the determinant. But I'm going to stop rambling and I'm just going to carry on. I'll put a timestamp like here, future Ivan, please do remember to put a timestamp so then you can just skip ahead, or I'll just make a chapters thing on a YouTube. But anyways, yeah, let's just get started. So we have matrix A. So if you want to find the rank of a matrix, you need to basically assume, especially or just for square matrices, that it's a full rank. So right now what we want to do is basically just assume the matrix A is a full rank of 3 because it's a 3 by 3. Its highest number of rows and columns in this case for a square matrix is the rank. So if you had a 4 by 4 matrix, the highest rank it could possibly be is 4. Okay, hopefully I made myself clear. So I'm just going to write 3 by 3 here, 3 by 3 and 3 by 2 just for our references. Okay, let's just basically find the determinant of A, and I'll get back to you because you should know how to find the determinant if you're watching this video. Okay, so I found the determinant of A of the 3 by 3 matrix, and my answer is -98. You can check that with me or check on an online determinant calculator, and you should get that this matrix has a determinant of -98. So as you can see, the determinant of A is -98, which is not equal to 0 because 98 and 0, or -98, sorry, and 0 are not the same number. So this essentially shows us that this has a rank of a full rank, sorry, of this matrix is a full rank because again 3 by 3. So here we can basically say therefore the rank of A is equal to 3, right? Because it's the full rank. So essentially the rule that I'm trying to show is that if a determinant of a matrix is equal to 0, this suggests that it's not a full rank. And the reason being is because if we think about the row reduction method, let's say we have 0, 0, 0 here, you would find that the determinant is equal to 0 because if one column is totally 0 or one row is totally 0, so it could either be that or it could either be that, you would find that the determinant is equal to 0, hence it's not a full rank, right? So that's what we found here. Moving on to B, we can do the same thing because again it's just a square matrix. You just find a normal determinant and that's basically it. So again, I will do that and I'll be back. So I found the determinant of matrix B, and essentially what we found is negative 120, negative 360, negative 360, and then plus 360, plus 360, plus 120. You don't even need the calculator for that. It will equal 0 because you have equal numbers on each side. So basically what we found is that the determinant of the full matrix, the 3x3 matrix of B, is equal to 0, and this means that the matrix B does not have a full rank. So you're probably wondering, okay, what do you do after this point? Well, once you've tried to find the determinant of the full matrix, you then have to assume that it has a rank of an n minus 1. So n is like your n by n matrix. So I don't know, n by n could stand for 4 by 4, 10 by 10, 9 by 9, and if you have the determinant of n is equal to 0, then assume rank of n is equal to n minus 1, right? So this is kind of like a dodgy way of writing the rule, but basically what I'm trying to say is if you found that the determinant of the square matrix is equal to 0, so in this case it's 3 by 3, assume now that the rank of B is 3 minus 1. So assume that the rank of B is equal to 2, and to verify that we would then basically find what I call minor determinants, which is basically finding a 2 by 2 determinant of every single 2 by 2 combination that you can physically have within inside the matrix. So what I mean by that is you find the determinant of this. If that is not equal to 0, you can stop there. If it's equal to 0, you carry on. You find the determinant of these, and then if that's equal to 0, you find the determinant of these. And if that's equal to 0, then you find the determinant of these. Oh my god, my voice, sorry. And if that's equal to 0, then you find the determinant of this, 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 and this together. Basically any combination of 2 by 2 within that 3 by 3 matrix, and if everything in that is equal to 0, you basically go down to 1, and you can instantly see that it's not equal to 0. So the rank, if in that case the rank of B would equal to 1. But let's try and find the determinant of this minor, or these components in B, right? So I will write it down here and just say, the determinant of B, and then put like a notation to show that, it's differentiated from this one here. So I'm just going to put a 1 just to mark, because maybe we have to do further determinant calculations later on. So we find a determinant of the 2 by 2, which here is minus 8, 2, 10, negative 2.5. I think I'm just gonna use a calculator not to risk it. So we have 20 minus 20, because you use Laplace expansion to find the determinant. So multiply or find the product of these and find the difference between this product, or the anti-diagonal, I think some people call it. And yeah, this equals 0, which means we have to do another determinant to check whether the rank of B is 2 or if the rank of B is 1. So we do determinant of, and finally we have a number which is not equal to 0. So sometimes, again, this is a little bit of a hit and miss, because someone, let me just tidy this up so it's a little bit less confusing. So for example, right, we started with these 4 numbers, right? That was really unclear, sorry. We started with these 4 numbers. Sorry, I just lost my page there. But anyways, what I was trying to say is that this is a little bit of a hit and miss, because we started with these 4 elements here. However, if you started with the bottom right 4 elements and you get the answer straight away, then you can stop right there. So it's a little bit of a hit and miss in terms of how fast you can get the answer, if you're wondering. But yeah, it's essentially just you attempt every single one until you get the determinant is not equal to 0. And in this case, we had to do it, well, basically 5 times, including this one over here. So yeah, it was a little bit unlucky. However, we did make it. And yeah, so we can now basically say, therefore, the rank of B is equal to 2. Again, just to make sure everyone understands, the reason why the rank is not 3 is because we found with the 3 by 3 determinant that the determinant is equal to 0, which means that we have to assume that the rank of B is n minus 1. So we then move down to find the mini determinants, as I call it, or the minor determinants, and you basically find the determinant of every combination of 2 by 2 within our 3 by 3 matrix. And when we did that, for the first one we got 0, second one we got 0, third one we got 0, and then finally for the bottom right it was not equal to 0, so therefore we have evidence to suggest that the rank of B is equal to 2. Hopefully that made sense, and we'll move on to rank of C, or finding the rank of C. Okay, so I've included the matrix C here because, as you can probably see, it is not a square matrix, and you're probably wondering, so how do I find the rank? It's not possible because, you know, a determinant can only be found in a matrix when the matrix is a square, which basically means there has even dimensions of rows and columns. So like our A and B, our n by n matrices, right now we have an n by m, which basically means we don't have the same dimensions for rows and columns. So essentially what you do here is you can't assume that the rank of C is 3. It's not physically possible, it's not feasible here because we have a 2 as our column. So essentially what you do is when you have an n by m, and suppose m is less than n, we need to assume that the rank of, let's say, x is less than or equal to m. Okay, so this is the general rule for an n by m matrix, which is what we have for C. So what we basically have to do here is assume that the highest rank C can physically be is 2, because we have 2 columns. So you basically look at the smallest row or column. So let's say it was a 2 by 3. You look at the rows and say, because it's a 2 by 3, the highest rank we can physically have is 2. So no matter whether it's a row or column, the smallest number always prioritizes the larger number, and that is what we will assume the maximum rank of that matrix can be. So once you've done that, you can then basically do something similar to what we did in B and find the minor determinants within that matrix. So here we would find basically the matrix of this and then the matrix of this, and if both of them equal 0, then we would carry on to find the matrix of just one element, and that's not equal to 0. So yeah, the rank would be 1 if in both cases this determinant and this determinant are both equal to 0. However, that's not the case right now. We can clearly see that here. Oops. We can clearly see that this is not equal to 0. So we can find a determinant of C, let's say 1, is equal to 22 minus 35, and that is not equal to 0. And thus we can say that the rank of C must equal 2. Again, it cannot be 3 because our smallest number here is 2, and it takes priority given this row over here. So yeah, not too bad as it seems, but yeah, just you need to understand when you go down in rank and when you don't, and when it's a full rank and when it's not. So hopefully that made sense and it cleared up a little bit of confusion. Sorry for my horrible voice and sorry for long-winding this video, but I just wanted to make it nice and clear. But anyways, if you guys enjoyed, please like and subscribe, and hopefully I'll be making more content in 2024. See you later.